In question 1, they tell us forces F1 and F2 are applied to the lunchbox as it slides at constant velocity. If we look at Newton's second law, F equals ma, constant velocity is 0 acceleration. So that means that if the acceleration is 0, the sum of the forces have to add to 0 in both the x direction and the y direction. Now the lunchbox isn't going to move in the y direction, so I know we're talking about the x direction. So F1 has an x component to it, F1x. And I know that for this lunchbox to have a 0 acceleration and move at constant velocity, F1x and F2 have to be equal in magnitude, and because they're in the opposite directions, they'll add to 0 if they are equal in magnitude. If we decrease the angle theta, the x component of F1, we know F1 cosine the angle. So if theta is getting smaller, the cosine of the angle is getting bigger. So that means more of the F1 force is going towards the x direction as we decrease this angle. So F1 is staying constant, but as it decreases in angle, more of that force goes to the x direction and less of it goes to the y direction. So if this is getting larger, F1x on the right side, F2 on the left side must also be getting larger, increasing in magnitude. Question 2. At time t equals 0, a constant force begins to act on a rock moving through deep space in the positive x direction. For times greater than 0, which are the possible functions for the rock's position? So we know that the derivative of position is velocity. And when I take the derivative a second time, I get acceleration. So for the first one, acceleration equals 0. For the second one, the acceleration is -8. And for the third one, the acceleration is +8. So a constant force produces a constant acceleration. So in choices 2 and 3, I have constant acceleration that is non-zero. And therefore, those are the ones that could be created by a constant force. 0 acceleration would be created by 0 force. So a constant force in the negative direction produces this acceleration, and a constant force in the positive direction produces this acceleration. So that answers our part B for us, for which function is F directed opposite the rock's initial direction of motion. So if it's initially going in the positive direction, choice 2, the negative acceleration is opposite the rock's initial direction of motion. Okay, question 3. We have overhead views of 4 situations in which forces act on a block that lies on a frictionless floor. If the force magnitudes are chosen properly, in other words, they can be whatever we want them to be, in which situations is it possible that the block is stationary? Well, if the block is stationary, it's not accelerating. Whoops. If the block is stationary, we know it's not accelerating, so the sum of the forces is mass times acceleration. If there's no acceleration, that means the forces have to add to 0. So that's what we have to ask ourselves. Is it possible for these forces to add to 0? F1 has both a y component and an x component. This x component and F2 could cancel out, but there's nothing to cancel out this y component of F1. So this cannot add to 0. So it is not possible that that block could be stationary. Here, F1 and F2, if we choose F1 and F2 to be equal in magnitude, they're opposite in direction. So yes, that block could be stationary. Over here, F1 has a y component and an x component. The x component of F1 could cancel out with F2, but the y component of F1 adds to F3, and there's no downward forces to cancel out with those. So this one cannot be have 0 acceleration or be stationary. Okay? Here, F1 has a y component and an x component. The x component could cancel out with F2, and the y component could cancel out with F3. So yes, that situation could be stationary. Moving with constant velocity means the same thing as being stationary in terms of Newton's second law. If it's moving, it'll keep moving. If it's stationary, it'll remain stationary when acceleration is 0. So the answers to part A are the same as the answers to part B. All right, question 4. Two forces are acting on a banana split. One force is plus x and negative y components. The other force is negative x and negative y components. So which of the vectors in the diagram best represent F1? Well, positive x and negative y. Positive x and negative y. It's either 5 or 6. Can't tell yet. F2 is negative 1, negative 2. So negative 1, negative 2. Comparing the numbers, I would choose 7 for F2 and 5 for F1. What is the net force component along the x-axis and the y-axis for the net force? Okay, well, here we go. We can add them up. F1 is 3, negative 4. And F2 is negative 1 in the I and negative 2 in the J. So when we add those up, I get 2 in the I and negative 6 in the J. And you could also get an idea graphically with the parallelogram rule. If you draw a parallelogram, not quite a parallelogram there. Let's fix that. There we go. And the net force is the diagonal of the parallelogram. F, sigma F. There's the sum of the forces and of force 7 and force 5. And we can see that has an x component of 2 and a y component of negative 6. So into which quadrants do the net force vector and the split's acceleration vector point? Well, the net force and the acceleration are always in the same direction. So the answer to both of those is the fourth quadrant. Question number 5 asks, in which situations does the object have acceleration in the x and the y directions? So acceleration is related to net force, so that's what we have to do. We have to find the net force in the x direction and the net force in the y direction. So for the first diagram, I have 3 and 2, that's 5 in the negative x, and plus 5 in the positive x. So for the first one, I have no component of force, no net component of force in the x direction. In the y direction, I have plus 7 and minus 4, so I have plus 3 in the y direction. For diagram 2, in the x, I have plus 3 and negative 2, so that's plus 1 in the x, and 6 and 6, 0 in the y. For the third diagram, plus 5 and negative 4 gives me plus 1 in the x, and 7 downward and 6 upward gives me negative 1 in the y. And for the last one, 3 and 2 in the upward direction, 5 and 4 in the downward direction, so that's 9 and 5. That gives me a net negative 4 in the y. And in the x, 3 to the left, 5 to the left, 3 to the right, for a total of negative 2. So those are my components of the net force, and in each situation give the direction of acceleration. So 0x and plus 3, that's going to be on the positive y-axis, in that direction of the positive y-axis. Plus 1 in the x and 0 in the y is going to be in the direction of the plus x-axis. Plus 1 in the x, negative 1 in the y is going to be the fourth quadrant. And negative 2 in the x, negative 4 in the y is going to be the third quadrant. Number 6, using the same diagrams from the past problem number 5, find out which velocity graph in the x and which velocity graph in the y best correspond to each of these 4 situations. So for diagram number 1, I had a net force in the x of 0. The sum of the forces is equal to mass times acceleration in both the x and the y. So if the forces in the x are 0, the acceleration in the x is 0. And which of these graphs corresponds to 0 acceleration? Well, this graph has constant velocity. So that's A. And in the y, I have +7 and -4. So a +3 in the y. So 3 Newton net force will give me a constant acceleration. A constant force of 3 newtons provides a constant acceleration. So the slope is constant and positive. So that's E. Okay, for the second diagram, in the x direction, I have +1 net, +1 Newton net force. So here we go, a constant positive slope. So that would be B. And in the y direction, I have +2 net force. So again, that will be diagram, hold on, 6, oh, I'm sorry, -6 and +6 gives me a net force of 0. So that means a constant velocity corresponds to 0 net force. So that is diagram D. For the third situation, in the x direction, I have +1. So that corresponds to a positive slope in the velocity. And in the y, we have 5 to the right, 4 to the left for a net, in the y direction, I have 6 up and 7 down. 4 + 3 is 7. So that's a -1 net force in the y. So here we go. This graph is a negative slope. So that's F. And the last one, in the x direction, I have net -2 in the x. So that would be this one. And in the y, we have a net negative force as well. So again, that corresponds to graph F for the negative slope here. Problem 7, we have these 4 blocks being accelerated by a pulling force over here, and the blocks are connected with cords, strings. Okay? What total mass is accelerated to the right by this force? Well, of course, they're tied together, they're all moving, so F is accelerating all of these blocks. So 5 + 2 is 7, + 3 is 10, plus another 10 is 20 kilograms. Is being accelerated by force F. What total mass is accelerated to the right by cord 3? This cord is only pulling these 3 blocks. This block is being pulled by this tension. So 3 only pulls 5 + 3 + 10, or 18 kilograms. And cord 1 is only pulling this block. These blocks are all being pulled by cord 2 and 3 and F. So cord 1 is only accelerating the 10 kilogram block. Rank the blocks according to their accelerations, greatest first. Well, if we assume the strings don't stretch at all, they're all moving at the same rate, so they're all accelerating the same. However, rank the cords according to their tension. The sum of the forces is equal to mass times acceleration. So if they all have the same acceleration, when there's more mass being accelerated, there is more force. In this case, that's tension. There's more tension required. So this cord has to accelerate all the masses. So its tension here is needs to be large enough to accelerate 20 kilograms at the given acceleration. So that's going to be the most tense, and then it's going to decrease. This one only has to accelerate 18 kilograms, this one only has to accelerate 13 kilograms, and this one only has to accelerate 10 kilograms. So this is the greatest, F is the greatest, followed by cord 3, then 2, then 1. Okay, question 8. A bread box where horizontal forces are applied. Rank the situations according to the magnitude of the box's acceleration greatest first. So of course we're going to use sum of the forces is equal to mass times acceleration. And it's important to note here that even though this situation has very large numbers compared to this situation, the difference between 60 and 58 and 15 and 13 is still 2 newtons. So the net force is all that matters. So here the net force is 3 newtons. Here the net force is 2 newtons to the right, 3 newtons to the right, 2 newtons to the right, and here 20 and 25 together is 45 newtons, 43 to the left, so it's 2 newtons to the right. So we see that situations B, C, and D will all have the same acceleration, which will be less than situation A, because in situation A we have more net force. So the answer is A is greater than B and C and D, which all 3 are equal. Question 9. A vertical force is applied to a block of mass M that lies on a floor. What happens to the magnitude of the normal force? So I've drawn the normal force vector. Here's the floor. As the magnitude of F is increased from 0. If F is downward, if F is downward and that increases for the sum of the forces to still equal to 0, don't forget about the weight, which I'll label with mg. So if this block is to remain stationary, F and mg together must be the same amount as normal force. So if F is directed downward and I increase it, that means the total net downward force is greater. So the normal force must increase to counter this increased force down here. Now if F points upward instead, now F and the normal force together equal the weight of the object. So if I increase F, the weight of course is not changing, so if I increase F, the normal force goes down. Written like this. The normal force and the pulling force together equal the weight. So if this one goes up and this stays same, this goes down. Okay, so here we've got a block on a ramp, and we have 4 possible forces. 2 of them are vertical, 2 of them are horizontal, and we want to rank each situation A, B, C, and D by which one has the greatest normal force down to which has the smallest normal force. So we're going to, a little trick about doing these incline problems is let the direction of possible motion be the x-axis. So if I draw this as the x-axis here, that makes this the y-axis, and there's not going to be any motion in the y direction. And that's helpful because then I can say the sum of the forces in the y equals to 0, because I know the forces in the y create acceleration in the y, but if there is no motion in the y at all, then I know the acceleration in the y is 0, and so the sum of the forces in the y is 0. In other words, any upward forces in the y are equal and opposite to any downward forces in the y. they cancel each other out and add to 0. So let's look at what are the forces acting on the block. Well, I've labeled them in orange here. The weight is always vertically straight down, and the normal force is the force of the ramp pushing on the block, which of course is normal to the surface of the ramp. So that is another reason why this tilted coordinate system helps me, because now the normal force is on the y-axis, and the y-axis is perpendicular or normal to the ramp. Okay, so those orange forces, or those orange vectors that show the normal force and the weight, I'm going to resolve the weight into its x and y components, and I only show the y component here because that's what I care about. I'm trying to find the sum of the forces in the y. And like I said, the upward forces will be equal to the downward forces, so they cancel each other out. Now, I've shown the y component. Be careful that it is a very common mistake for students to show the y component like this. They'll draw a horizontal line over to the y-axis. Be careful, that's not correct. Okay? The y component, you must draw perpendicular to the y-axis. Okay? So that this here is a right angle. All right? So that's my y component of the weight. Now let's pick one of the forces that we're going to analyze. Let's choose force A. Okay? So where's the y component of A? And again, make sure you draw over to the y-axis so that this is a right angle right there. Okay, so that means let's use a different color actually for A. There is the y component of A right there. So I'm going to call that AY. All right, now let's look at the sum of the forces in the y. I have the normal force and the A component of y, and they're both in the positive direction. So they have a positive sign that associated with them, but the y component of weight is in the negative direction, so it has a negative sign. And those three forces add to 0. So if I solve that for the normal force, I see that the normal force is the y component of weight minus AY. So for a second, let's pretend A is not there. If A is not there, there is no y component of A, and the normal force is equal in magnitude to the y component of weight, and of course they point in opposite directions. But when A is there, now I've got this y component of A that takes away from the right side of the equation. It makes the right side of the equation become less. So the normal force is becoming less when A is there. In other words, the y component of A is helping to oppose Wy. So there doesn't have to be as much of a normal force because the upward forces have to equal the downward forces. So if I have this AY present, then Fn doesn't need to be as big. Likewise for B, if I draw over for its y component, and again, let me use a different color. I'll use green, okay? For B, if I draw that over, now my By is there. And when I do the equation, now this term becomes By. And I notice that the y component of B is larger than the y component of A. So that means this right side of the equation is going to become even smaller. Okay? So Fn is going to be even less. It makes sense because if By is bigger than Ay, By is helping to oppose Wy more, and so Fn is less. Now let's look at C and D. D's y component is there. dy. Okay? So if I do my sum of the forces in the y now, I have Fn minus dy minus Wy equals 0. And I solve that for the normal force. I see that the normal force now is greater than the y component of the weight by this much. In other words, if D has a component of force that's pushing the block into the ramp, Fn has to work harder or push back more to offset these downward forces. Remember, the downward forces equal to upward forces. So if I'm increasing the amount of downward force by dy, that means the upward amount of Fn has to increase as well. And again, if I do it for C, there is Cy. And the equations would look the same because Cy is in the negative direction. I would just replace dy with Cy. And since Cy is less than dy, that means Fn will be less with force C than it is with force D. So to rank them then, ranking by normal force, D caused the greatest normal force, then C next, then A, and B had the least normal force.